Let's talk about decision trees. So, class decision tree extends supervised learner. That's a little humongous. You're going to write something that looks kind of like this-ish, right? Okay. You're going to have some type of a train method and some type of a predict method. And if I recall correctly, the predict method takes a vector of features as input and outputs a vector of labels. And your train function probably takes a matrix of features and return, and also a matrix of labels. Now, I've already provided a node class for you, so we'll just assume that already exists. How do we train a decision tree? Here's the idea. You've got a bunch of data, and we want to recursively chop it up to make a tree. So we're going to need some type of tree here. So let node root be a node, and now we're going to train it. So how about we'll say root equals build tree feet lab, and the only reason I do that is so I can make it recursive. So let's do that. Now this will have to return a node instead of a root. Somewhere inside of our build tree, what are we going to do? Basically chop the data. Let's be slightly more specific than that. Let's say, how about int column equals pick dividing column from your features and your labels. And then we'll say double pivot equals pick pivot from your features and your labels. And then we're going to divide the data. How do we divide our data in half, assuming we've picked a column and a feature? It'll look something like this. I'll pass in my features matrix to the constructor. Here's what I'm assuming this means. I'm not copying my features matrix. I'm copying the metadata out of my features matrix, because I want this matrix to have the same number of columns, each with the same number of values in each column as the features matrix. And I'm going to make another one called feat2. I have created 4 empty shell matrices. Why? Because now I'm going to fill them up with the stuff that's inside of these features and labels. So let's suppose let's just start dividing the data. So int I equals 0, I is less than feat.rows I plus plus. And by the way, just as good programming practice, you should probably do something like this. If feat.rows is not equal to lab.rows, throw new runtime exception, pretend I spelled it right, mismatching features and labels. Why do features and labels have to have the same number of rows? Because these are example inputs and outputs for the function that we're trying to learn. So if for every pattern you have the corresponding label that you're trying to predict, that makes sense. If they don't have the same number of rows, what are you doing? Right? With me? Okay. So I'm already assuming they have the same number of rows, and I've checked it right there. And I've already picked a dividing point and a pivoting point. I don't know if those are technical terms, so I don't know if the word pivot is actually used in decision tree literature. It's probably not, so don't lean on that term. But here we are. We're going to now start dividing it. I need to know whether or not this column that I've decided to split my data on is continuous or categorical. Why? Because that's going to affect how I split it. So how about I say int vals equals feat dot value count of call if vals is 0. So if it's a continuous attribute that we're splitting on, then we're going to do one thing. And if it's a categorical attribute that we're splitting on, we're going to do another thing. Let's suppose it's continuous. Then I'll say if feet of I of, yes, we're doing row I column call. And now I'm switching into C++ syntax. So if that is less than the pivot, then we'll say feet A dot take row of feet dot drop row of I. And we'll do the same thing with the labels. Otherwise, feet B. Do you see what I am doing right here? I'm taking all of my data, and I pick some way to divide that data, and now I'm running through all of the rows in that data, and for each row I'm going to say, hey, which side of the division do you go down? Do you go down this side of the division, or do you go down that side of the division? And I'm assuming this drop row method just causes this matrix to release at that row. So now I have the pointer to it, and I'm just going to say take row, puts it into this matrix, and by the time this for loop is all done, my feet and lab matrices will have 0 rows remaining in them, right? Whereas my feet A and feet B and lab A and lab B matrices will now contain all of the data. And so essentially I have divided the data. You'll have some code somewhere that looks something like this, and you'll also write the categorical equivalent, which instead of checking for less than, it checks for equivalency. And basically, I've just cut the data in half. Well then, suppose I have divided my data in half. What do? Well, I say node A equals build tree of feet A, lab A, and node B is build tree feet B, lab B. And now I have 2 nodes, and then I can say return new interior node that takes A and B and call and pivots. And essentially, I have just written a decision tree builder. Now, immediately, your coding instincts are saying, wait a minute, there's no base case, this will recurse forever, this code has all kinds of problems, right? But I wanted to give you the basic architecture just so that you know kind of what you're doing at a high level. And now let's kind of fix the problems so we can be a little more practical and make this tree actually work. I don't know if I actually supplied this method for you. I think I might have. Nobody's checked yet?
Yeah, it's called remove row.
It's called remove row? Okay, there you go. If I did, here's how I would have written it. When you remove the row, it's going to swap it with the last row. And then it's going to remove the last row because that's a really efficient operation. It just decrements the size by 1 and returns the reference to the row to you. So it's actually a rather efficient operation to remove a row. And then take row is just going to be the equivalent of pushback, or it's going to add to the dynamic array. And so this whole operation should be efficient, and it just basically moves the row from one matrix to the other matrix. A lot of students implement this stuff by actually copying the row rather than moving the row. If you want to do that, fine, but when you start working with really big data, it's going to be inefficient. So this is my attempt to kind of nudge you in the direction of, hey, let's write this thing to be fast, because one of the awesome things about decision trees is they're friggin' fast. So don't you want a nice implementation of one so you can work with big data and participate in the whole big data revolution or something like that? Here's what I have done. This whole thing is recursive, because right here when I say root equals build tree, I'm really saying, hey, take the data and just chop it up infinitely forever. That's a problem, because what if you can't actually divide the data? We need the case of a leaf node. So let's suppose we did divide the data, and then here we say, if feet A dot rows is 0, or feet B dot rows is 0. This basically means we failed to divide the data. If that occurs, then return new leaf node that is made out of the labels of, I'll just pass in my features and labels matrix, and I'll assume that the leaf node constructor actually goes through and, actually you don't need to know the features for that. We're going to assume that this leaf node constructor just computes the mean of all of the continuous values in the label matrix and the most common value of all of the categorical attributes in the label matrix. Okay, well, I'll just explain it for convenience here. Suppose you have these numbers. You started with a data set of thousands of people, and you knew all their shoe sizes, and you knew all of their IQs, and you kept chopping them down, and it turns out that finally you ended up with all of size 12B shoes, and these are the people that had size 12B shoes, and those were their IQs. That's kind of sad. They're all pretty mediocre. I would expect more variance than that. Well then, later on in the future, you see somebody with size 12B shoes. What do you predict their IQ must be? What's the most intelligent prediction you could make based on the data? What's that? About 100? Yeah, that's probably honest, but the data says it's really 102 plus 100 plus 96 plus 104 plus 103 divided by 1, 2, 3, 4, 5. 101 is a slightly better answer. It is about 100. But 101 is what the data says is the average for people with size 12B shoes. Now, if it were exactly 100, that would imply there's probably no correlation between shoe size and intelligence, which is what I predict. But I haven't actually done this experiment, so I don't know. Maybe there is a relationship. Let's hope not. Let's suppose then you're trying to predict based on shoe size hair color. And after you chop up your data, you finally arrive at everyone with size 12B shoes, and their hair colors are black, 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 blonde, and black, and red, and black. Then you encounter some other person with size 12B shoes. None of them have brown hair. That's how odd. But you encounter somebody else with this size of shoe. What's the most intelligent prediction you could make for this person? For their hair color? Black. The answer is black, because the data says most people with that size of shoe have black hair. Now, this was a stupid example because shoes are not predictive of anything, but if you had enough information, if you knew their shoe size and their collar length and their, I don't know why I'm doing measurements, and their temperature and their father's occupation and their zip code, then you know what? All of a sudden, it starts getting weirdly, you start being able to predict things that you might not think you would be able to predict. Because it turns out, zip code says a lot about income, and it turns out income says a lot about education, and it turns out education does have a lot of correlation with IQ. And it turns out that your zip code does say a lot about your ethnicity, which does say a lot about your hair color. So you can see that while shoe size might have nothing to do with these things, if you have enough features, the machine might be able to find correlations, even if they're correlations you're unaware of, right? And so when we make predictions, if your labels are continuous, you want to predict the average value. If your labels are categorical, you want to predict the most common value. And as it happens, if you will look, this is the baseline learner that I provided to you. Well, basically, to train it, you pass in features and labels, and it computes for continuous values the mean, and for categorical values the most common value. Do you see how there was a subtle being helpful in providing this baseline algorithm for you? Because it kind of does exactly what you're going to do at the leaf nodes of your tree. So right here, when you're constructing a leaf node, just kind of do what baseline does. In fact, you could say the leaf node is the baseline of the remaining labels from what we've chopped down to that point. Does that kind of make sense? Well, now I think we have a barely functional decision tree. How are we going to make predictions with this thing? Something along the lines of this. While true. And then I'll say node n equals root. Then I'll say if n dot is interior node, else lab dot copy n dot labels. Something like that. So I have just made a tree runner. It's going to start at the root, and it's going to run down the tree until it hits a label, a leaf node. And when it hits the leaf node, we'll copy the labels into lab, which is our return value. In fact, why don't we just stick it right here instead? And we could actually return it. Then I could just do that type of a thing. However you want to structure it, that's fine. You might want to change my interface. You might have to mess with the baseline algorithm to make it work. I don't care. Pretend this code is your code and hack it to pieces. You don't have to be constrained by anything I provided. And then inside these interior nodes, I'm just going to say if feature of n.call is less than n.pivot, then n equals n.a, else n equals n.b, something like that. Do you see that this basically runs down the tree? That's about all there is to it. Here are some issues that will come up with this code. One, well, I didn't do the categorical ones. There, you've got something to do on your own. Let's talk about picking the dividing column and picking the pivot. Which is a better tree? One that looks like this, or one that looks like this? The answer is the balanced tree is probably better, right? And why do we think it's better? Because it feels better, it takes less time to get to the leaf nodes, so it's more efficient. But in machine learning, we're generally not that concerned about efficiency. We're usually much more concerned about accuracy. Which one do you think is more accurate? Imagine that little ball that you place 20 questions with you, and imagine that it's trying to find out what you're thinking about, and it does by saying, are you thinking about a gorilla? Are you thinking about a walnut? Are you thinking about a school bus? Are you thinking about a turtle's shell? Are you thinking about a tack stuck into the bottom of somebody's shoe? Are you thinking about Spider-Man's web? Are you thinking about the Death Star? Do you see how that's this tree? It's really just ruling out, is it this obscure thing that would be a leaf node? No, if not, go to this unobscure thing. And what is this tree represent in the context of this 20 questions ball? Kind of, is it alive or dead? Yeah. Is it on this half of, is it north of the equator or south of the equator? Is every question it asks is trying to divide your data in half. How can we make a tree look like this and not like that? Do you see that when we make a division, we really want to divide the data well rather than poorly? We want to get, maybe half on this side and half on that side. And more specifically, imagine that we had data that looked kind of like this, and you want to separate the red from the blue points. Which one's a better division? The one that does it about half 50-50, or the one that does that? Obviously this is the better answer, right? So do you see that it's not really based on the points? It's not based on, you don't want 50% of the features on one side and 50% of the features on the other side. What you really want is homogeneity in the labels. And the labels are what you're ultimately trying to get at. Okay, how can we measure homogeneity in labels?